Now let's see how addressing is done in an internet, and we will do this at hand of the IP protocol version 4. We already discussed that information are sent in form of data packets through the internet. The internet, that is an interconnection of different networks. Each of the networks, there is a hardware address for each host, for each computer that's assigned to such a network. But what we need in the interconnected network is a unique address that it's unique not only, like in case of the hardware address, unique in the local network, in the physical network. What we need is an address that's unique in the interconnected networks. So an important thing Internet Protocol has to solve is to design an unique address scheme so that we are able to assign to each host that's connected to the internet a unique address. This standard that's defined by the IP protocol, we have to distinguish between IP protocol version 4 and IP protocol version 6. So let's consider the standard for the IP protocol version 4, assigns to each host a 30-bit number. 30-bit number, so we have the chance to assign 2 to the maximally 2 to the 32 different addresses. So the 30-bit number, that is for the communication in the internet, so each of the hosts gets assigned such an IP address. IP address, Internet Protocol address. So each data packet that's sent through the Ethernet to the internet is assigned at least 2 addresses: the address of the sender as well the IP address of the receiver. The 32-bit IP address consists of 2 parts. One part, first part, is a prefix. The prefix is used to address, to identify the physical network the host belongs to. And then the suffix, second part of the address, is used to identify the specific computer inside the network. This subdivision makes it possible that for the routing, the first part of the IP address says to which network the data packet has to be sent. And then if the data packet has reached this network, this local network, the second part of the address tells which of the hosts, which of the computer connected to this network is the receiver of the data package. So if we look carefully, the IP address does not specify a computer. The IP address specifies a link from a computer to a network. This is important to realize because a computer which is connected to different networks, for example like a router, needs different IP addresses. Because first part identifies the network. Second part identifies the suffix, identifies the specific computer in the network. So this is a general scheme of an IP address, prefix which gives the network ID, and suffix which gives the computer ID. Now the question is how many of the bits we assign to the network address and how many bits from the 32 bits we assign, we use and reserve for the computer ID. And that's a difficult question. If we have a fixed length of the prefix and a fixed length of the suffix, then we can, let's say, we have length n of the suffix and 32 minus n for the computer ID, then we can assign to an internet exactly, to an IP version 4 internet, exactly 2 to the n different networks. And each network we can only design 2 to the 32 minus n. So in the very beginning it was clear that that's not a good concept to have a fixed boundary between the prefix and the suffix. Instead, the following scheme was used, the so-called class-full addressing. The IP addresses space was divided into different classes. So we have class A addresses. Class A addresses every time start with a 0. Then 7 bits are used for the network ID, and the remaining 24 bits are used for the suffix for the computer ID. So such class A nets, it's a relatively small number of networks, 2 to the 7. And each of this network can be very large with 2 to the 24 different computers connected to this network. So this is an address type that's specified for use in huge local networks. There are many smaller networks. So a second class, a class B IP address, which can be recognized considering the first 2 bits. It starts with a 1. It needs to be start with a 1 to differentiate it from class A networks. And then a second bit is used to identify this is in class B address. And then we have 16 minus 2, 14 bits to define network IDs, and remaining 16 bit to define a computer, the host ID. So this type of class B networks, there could be many of this class B networks, 2 to the 14 different class B networks, and to each of these class B networks, maximally 2 to the 16 different hosts may be connected. So this is a middle-size network. And then there is a class C network. Class C, to differentiate it from the class A, and class B starts with 2 1s. And to allow further distinction to other classes, then comes a 0. And then 24 minus 3. So 24 minus 3 is 21 bits are available to define network ID. So we can have 2 to the 21 different networks. And each network can have maximally 32 minus 24, so 2 to the 8 computers connected to it. So the number of bits, so if this is 8, so we have 2 to the 8 different possibilities to define host IDs. So you see, we have with class A addresses the ability to define network IP addresses for a relatively small number of huge networks. We have class B addresses to address mid-size networks, class C addresses to define many of relatively small networks. And then there are 2 more classes, class D and class E, for multicast addresses and reserved. So this was a historical concept because it was not useful to divide the address space by a fixed boundary between the network ID and the suffix, the prefix and the suffix between the network ID and the host ID. The way IP addresses are written is done is the following. We have 4 groups subdivided by dots. And of course, 30-bit is a whole address. So each of the 4 groups has length 8 bits. And with 8 bits, we can exactly describe numbers in the range of 0 to 2 to the 8, 2 to the 8 minus 1. So here we have an IP address, 32 bits. It's difficult to remember this, so that a human can communicate such IP address. We subdivide the 32 bits in 4 groups of 8 bit keys, and then we interpret the 8 bits as a number in digital system. So in each of this group, maximal, we can have a number between 0 and 255. Here are some examples of some very special address, so-called loop-back address. It's needed for testing, so it's not using the internet at all. We have the network ID 127 and the host ID 1. We have private addresses defined in RFC 1597. They look following. They start with 10 dot, and then we can have different numbers. Then the range 122.16.0.0 up to 122.31.31.254. These are examples of private addresses. Let's have a look on an image that shows an interconnection of different networks. Here we have a huge network with many, many computers, and the addresses that are used are class A networks. So here the network ID is 17 dot, and the 3 more groups can be used to describe host IDs. So here are examples of different hosts belonging to this network, which class A IP addresses. Of course, in this network, each computer has also a hardware address, but for communication in the internet, for sending data through the interconnection to the virtual networks that are designed by interconnecting different networks, one needs the IP address. So each of these computers has at least 2 addresses, the hardware address and the IP address. This class A network, for example, is connected via an intermediate system, via a router, to a class B network. In a class B network, the first groups of numbers are used to define the network. So in this example, 134.23. The last 2 groups remain to assign numbers to the computers connected to this network. So for example, 1.55 or 203.5. There is another router connecting this class B network to a class C network to have also another example. Here, 3 of the groups are used to define the network ID, and the remaining digits are used to design the computers connected to this network. So this is an example of an IPv4 addressing. It is the historical way where we have different classes of computer, and this shows you that if you are a company or a private person, one has a small network, then one works with class C addresses. If there is a huge company or organization, then this class A, they should use class A network. Now we have to look for multi-homed hosts. I mentioned this already when I said that IP addresses does not identify computers. IP addresses identify a link between a network and a computer. So here, for example, we have a router, an intermediate system that connects these 3 networks. So this router is part of this network, the class A network. This router is part of this class B network, and the router is same time part of this class C network. To be part means that this computer can be reached as member of this network with an IP address start with the network ID 70. So what the computer needs for to make clear that it's connected to this class A network with the ID 70, the computer needs an IP address from this network. But same time, this router, because it is also a part of the class B network or a part of the class C network, it needs IP addresses from this network, where the network ID starts with 134.23, and it needs an IP address that starts with this network ID, and this is what is called a multi-homed host. The problem with this approach, I mentioned it was a historical problem, is that if we look to the theory, then the question is what happens if the infrastructure is changing. For example, if two companies with different networks are merged, then they want to have a common network. Or another example, a company starts as a startup with a small number of computers, then the company is very successful and wants to enlarge the network beyond the class C address as class C address type. So that means if they want to connect to their own network more than 256 computers. And this is a situation that occurs in practice and not very seldom. So one idea is if the network is growing beyond the boundary set by the available IP address, that network can start to use new address, so with a new class of address. That means that all the hosts need a new IP address. For example, if the class C network is too small, there are more than 254 hosts, the company wants to connect to their network, then they order a class B network. But this provides space for many more computers. But first problem is each computer needs a new address. So each router, each intermediate system in the internet needs to get a new information about this new address. But there is another problem. The next class, the class B network, that allows to connect 2 to the 16. It allows to connect 65,000 something host to it. And of course, between 254 and 65,000, there is a wide range. And a solution to this problem is that one starts to weaken this concept of network ID and host ID. And we will discuss this. So in a one sense, it's the subnet addressing to allowing to subdivide nets, and the other is the classless addressing or the supernetting. And let's have a closer look. Last possibility to solve this problem is to work with network address translation mechanism. Let's start with the concept of classless addressing, the so-called subnetting. Subnetting, that's the following. Logically, a network is divided into separate, physically independent subnetworks, subdivision of such class for addresses. The idea is that the provider can take a class B network and subdivide it into subnetworks which can be used by different companies. And the idea is the following. Here we have the boundary of the network, and now there are the range for the host ID. If we speak about this class B net, then there are 16 bits to describe, and the idea is to subdivide this host ID in a subnetwork ID and in a host ID. So not to take all the 16 bits to describe a host ID, but to take a few bits to describe a subnet, and the rest to use the host belonging to the subnet. So subnet ID, for example, with 6 bits, allow that one can have 62 subnets, and each of the hosts ID, there are 10 bits remaining, so each of the subnets can have about 1,000 hosts. So how the routers can detect that not only the network ID describes the network ID, but also the subnet ID needs to be considered to find out what is the right network ID. And there is a mechanism used which is simply to implement, and that is the mechanism of using subnetwork mask. And this subnetwork mask can have variable lengths. And the idea behind is the following. Here you can see the subnet mask in the description, and that means the following. We have an IP address where the network is described by 24 bits, and then we have the 7 bits that are used, the 8 bits that are used for describing the host. To make clear that this part of the address is used as a subnet ID, we compute an AND with so-called subnet mask, which has exactly 24 1-bit, and the remaining 8 bits are 0. To compute an AND of these two vectors, you remember AND 1 and 1 is 1, 1 and 0 is 0, leads that here from this subnet mask, the routers know this range is a range of the network ID. And the network ID, by computing an AND, is exactly this sequence. And this part, that is the host ID. And as long as the router are computing the network ID, having here all zeros has an effect that if the router computes an AND in conjunction of these two vectors, then all is vanished what is in that part. So only the network ID is remaining after computing an AND of these two vectors. So this is the idea of working with subnet mask. Subnet mask /74 shows that there are 24 1-bits helping the routers to find out what is a range to be considered as a network ID. And having here zeros results in that all the host ID part vanishes. This subnetworking must, in this sense, allow to have variable boundaries between network and host ID. In the historical approach with the class A, class B, class C net, this boundary was fixed. And the first bits are used to tell the router, this is class A, this is class B, this is class C address. By means of this subnet mask now, one can have any size, any length to use for the network ID, at least in principle, and the remaining part for the host ID. And the communications, the information for the router, what the router have to consider as a network ID, they get by means, they can compute in a very simple way by means of the subnet mask. So the router identifies a subnet via an associated subnet mask. Here let's take it in a mathematical way. We have the IP address, and we have the router has a subnet mask. And this is considered to be the subnet ID. This was the end of the subnet mask, so only the network ID part remains. The host ID vanishes. And if the IP address is conjuncted, if an end is computed with the inverse of the subnet mask. And the inverse of the subnet mask is a bitwise inversion. So if there is a 1 in the subnet mask, there is a 0 in the inverted subnet mask. And if there is a 0 in the subnet mask, there is a 1 in the inverted one. And then, of course, the subnet ID is vanishing, and only the host ID remains. So in this way, in a simple way, make an end computation with a subnet mask. A router can find out the network ID, and if the router needs the host ID, it makes a conjunction with the inversed subnet mask. The subnet masks are typically described in the following way. There is a dotted decimal notation you cannot see here. This means that all these blocks are consisting of ones. Yeah, this is a 2 to the 8 minus 1 is 255. And a more simple way is the CIDR notation. I used it on the last slide. There is a slash after the IP address, and there is a number, and this number is interpreted as that part of the subnet mask which consists of ones. So this was the way how we can subdivide networks into subnetworks. In other situations, one wants exactly the reverse. One wants to combine different networks to a common larger network. And this is called supernetting. And that's the complementary approach to the subnetting approach. Here, individual networks are combined to a supernetwork to reduce table entries. And the idea in which way this is solved is that continuous address blocks are used for this supernet, so-called CIDR blocks. So here is the RFC description of this classless interdomain routing. So the entry 139.199.32.0, 3 specifies 3 network classes. The class 0, you see this, the class 32, the class 33, up to the class 34. This combines the 3 address blocks. These are completely indifferent address blocks. Because of having it continuously succeeding, then the number 3 shows how many of these blocks are combined. Then we have this supernet. And if we describe this in a way with our internet, with our significant address bits, so we see, but also here by means of an internet address mask, which puts the first 22 bits to set to 1, then exactly these 3 networks are considered as one network address. Let's have a look on the third possibility to deal with the problem that the wished number of hosts belonging to a network does not fit to the address classes. This is the so-called network address translation. The network address translation is also very important in allowing mobile systems, smartphones, to connect to the internet. And the idea behind is that there is a so-called private IP address space. This private IP address space needs no more unique in the world. In each network, people can have their own private IP addresses, and these private IP addresses, they can also be used in another part. But the problem is, because there is no uniqueness guaranteed, this private address are not allowed to use to move in the internet. So the private IP addresses may only be used internally inside a network. And then in the boundary of the network, there is a router, the so-called net router, the network address translation router. And this network address translation router translates an internal, a private IP address into an external one, into one that's unique all over the internet and that may be used for internet communication. So you see, the idea behind this that with a few external addresses, a large network with private addresses can be put in a situation that these people with a private address, in the moment they have an external communication, they get an external IP address borrowed. So to organize this, TCP source and destination ports are used for unique identification. So here you see this is an internal net, a private network. There are IP addresses used, this private IP addresses. Please remember when we introduced the address classes, there was this block for private network addresses. These are real IP addresses, but they are allowed only to be used internally because each network administrator can assign same private address to different computers inside the network. Of course, the assignment of the private address inside the network, that need to be unique. So, and if this computer with this private IP address 10.1.21.25 wants to send a package to the internet or wants to contact someone outside the internet, then here in this net router, this private IP address is assigned to this external address. This external address is not a private address. That is an address that is unique in the internet that exactly describes some computer outside. But in this way, many computers with many different private IP addresses can use same external address. Of course, for each one doing simultaneously communication with the internet, they need different IP address. But in this way, the relatively small number of usual IP addresses that are valid worldwide can be used to serve for a big number of internal private networks. Of course, it's not trivial to organize this, and this is what the net router are working for. The net router needs a table which remembers exactly that this computer with a private network address was using that external usable address in that moment. So as long as in use, this external address cannot be assigned to any other host. But in the moment this communication is finished and another host with another private IP address wants to go to the internet, the net router can make a new assignment of an external address to such an internal address.